Hello everyone, my name is Delmar Cabral and I'm a graduate student Professor Victor Batista Group, part of the Center for Quantum Dynamics on Modular Quantum Devices. Today I'm going to describe how we can perform the simulation of the dynamics Heisenberg model using IBM quantum computers. The code that is going to be the focus of this presentation will also be made available at the website, and feel free to follow along as you listen to this presentation. To start, I'll describe what this Heisenberg Hamiltonian can be used to model. So we have a set of on-site parameters that describe the configuration of the spin state at any given site, given by the sigma z term, and then the coupling between adjacent spins given by these couplings along x, y, and z components. If we were to simulate the dynamics of this system, we can observe how an initial state of the system can evolve into a completely different configuration according to the parameters of this Hamiltonian. As example chemical system that can be used to describe, or that can be described by the Heisenberg model, is a graphene random ribbon and studying the magnetization of radical pairs at each side of these graphene nanosheets. So if you were to have this radical pair, their dynamics could be described by the Heisenberg model and define the probability of flipping the spin at each given site in this nanoribbon, or the configuration of any given site affecting the configuration of neighboring sites, or over the long range of the simulation. And if you were to describe the overall magnetizability over time, you could obtain the dynamic evolution of this particular system. So to bring this connection more closely, think about that each of these radicals at each site has a transition energy between the one spin state and the other, given by this omega n, which is the on-site coupling. And then the interaction between this radical on a given site with one in an adjacent site will be given by these j n plus 1 terms. And this allows the spin state of any particular site to influence those on another site, and therefore affect the overall magnetizability of the system. These parameters here listed on the left are the ones that are going to be used throughout our simulation, where we take 3 spins in our chain and the set of different parameters that describe the on-site and off-site couplings. So how is the time evolution performed? So we take the Hamiltonian corresponding to Heisenberg model, and we take the complex exponential of it multiplied by a time interval t. We implement this exponential of a matrix using the Trotter decomposition, and we decompose these terms in the Hamiltonian into even and odd components, where even designates even sides and odd sides. And this allows us to split this operator into different terms and apply them iteratively to our initial state that we define at the beginning of the simulation. For this simulation, we need a couple of different libraries that we're going to use in the Python framework, and all based on the Qiskit library from IBM. To create a Hamiltonian, we need a particular set of operators that define the terms in our expression. For the time evolution operator, we use the built-in Pauli evolution gate. For the Trotter implementation for the time evolution operator, use the Suzuki Trotter module. And then we need to create and execute a circuit, and we have different utils that allow us to accomplish this. So to construct a Hamiltonian, we proceed by building it term by term. Take as an example this y term between site n and n plus 1. We're going to have a string of identity matrices, and the yn and the yn plus 1 term on the associated sites. We take the outer product between all these matrices to obtain the overall operator affecting sites n and n plus 1. However, when we call this function in Qiskit, sparse Pauli op, we just need to provide the string that represents the sequence of these matrices. And if we know the index at which we have to apply the y and y terms, then we just need to prepend and append with the correct number of identity matrices. Similarly, we can construct all the terms associated with this given site n by providing the XX, YY, ZZ, and Z terms and the associated coefficients for each particular term. To construct the complete Hamiltonian, we need to take all these interactions for a given site and put them all together to describe the complete spin chain. So this is what this function accomplishes by supplying a number of qubits and a list of coefficients that is going to be used to populate that Hamiltonian. We obtain a sum of the even and the odd terms, and we return a list containing both. To construct the time evolution operator, we expect to know the number of spins in our chain, the time step tau, and the number of Trotter steps, alongside the number of coefficients. This matrix is going to call the Heisenberg Hamiltonian construction function, and then use a poly-evolution gate on this Hamiltonian, a small time step tau, and then perform the Suzuki-Trotter decomposition to second order, repeat a number of Trotter step times. So this allows you to decompose this tau into a small enough time step such that our approximation of this matrix exponential will yield a suitable representation for our time evolution operator. We return the definition of this operator object, which has this form here on the left. So essentially applying the even terms, the odd terms, and then the even terms with the associated Heisenberg Hamiltonian terms. And this on the left is how we'll call this particular function for the specific set of parameters it requires. So if you supply all the arguments, you can generate something like we have on the right side. Now we have the Hamiltonian, we have the time evolution operator. Now we need to construct a quantum circuit object that is going to perform our evolution of a given initial state. So we just call this quantum circuit function, supplied a given number of quantum bits, which are going to be used to execute our simulation, and the classical radius is going to be used to record our results. If you were to measure the state of the system at this time, you'll get the vacuum state. However, if you want a different initial state, then we need to instantiate it. So we can perform this initialization by bit flipping. Suppose you want to have the spin up, spin down configuration. Then you can keep the first qubit as is by applying the identity matrix, and then using the X gate to flip the bit state on the other two qubits and obtain the down configuration. Alternatively, you can use amplitude encoding to generate any arbitrary initial state as follows. If you call this initialize function and you provide a given string containing the, or a matrix containing the amplitudes associated with each qubit in the system, then you can perform the initialization of the quantum circuit to that particular state. In this case, we just pass 0, 1, 1 to obtain exactly that spin up, spin down configuration. So now that we have the initial state, we need to include a time evolution circuit. So recall that you construct the time evolution operator by calling this get time evolution operator function with the appropriate set of parameters to generate the time evolution operator on the right side. We can now apply this entire circuit, called here circuit 146, after our initial state. And this is going to evolve our initial state to a desired final state after some time tau. We can include this time evolution operator by just appending the time evolution operator to the respective quantum bits in our quantum circuit. We can include the measurement operation, and we can record this time evolved state after executing the circuit. So how do you actually execute? We need to specify either a simulator or a real device. In this case, if you want to provide a simulator backend, you can specify a method, in this case state vector, of the AIR simulator, which contains all the simulator backends available within Qiskit. Or if you want a real device to be used, then you need to import the IBM queue to access all the real devices. you need to supply your account credentials. And to do so, you'll need to have an IBM account created. You can list all available providers and list all the available backends within that particular provider. In this case, I'm selecting one of those that are available, IBM Cube line, which is going to be used to execute the circuit. If you want to execute on the backend, the syntax after this is exactly the same. You need to apply measurement operations to your quantum circuit, transpile to that particular backend, whether it's the simulator or the quantum device, specify an optimization to have a better translation of your quantum circuit into this particular framework of the backend, and then specify the number of times you want to execute, in this case 1,000 times, and store the result of that operation. Once you have the result, you can obtain the number of counts that you measure each state in your quantum device and obtain the statistics associated with your circuit execution. So in this case, once the simulation has been performed, in this case using the state vector simulator, and we calculate the survival amplitude by projecting the final state to initial state and squaring, we obtain the results that agree to a very high degree with our benchmark. So the results using the state vector simulator, based on all the preparation we did priorly to this slide, are shown in green, and all the benchmark are shown as the line. And we can see a complete agreement between all of these. However, if you want to execute this on quantum hardware, you cannot use this method of executing and recording the complete final state. So to do this, there's an algorithm called the Hadamard test that allows to obtain the real and imaginary components of any unitary operator U and generate this for any arbitrary quantum device, as long as it has this particular format. So in this case, we have a set of qubits associated with our initial state, to which we're going to apply our unitary operation, in this case our time evolution operator, conditionally to the state of our ancilla qubit, which has been prepared in a superposition state. So if this state has the value 0, nothing is going to happen to the initial state qubits, but if it is 1, then we apply the unitary operation U, and then we perform or undo the superposition on the ancilla and record, and this allows to obtain the real component. Similarly, we can calculate the imaginary component of our unitary operator by including an additional phase operation in our ancillary qubit. So the results of this Hadamard test are going to be dependent on the measurement of the ancilla in the sigma z basis. So if we have the 0 state and we perform the sigma z expectation value, you obtain the eigenvalue of 1, and if we have 1, we obtain -1. So if we account for the number of times that we measure 1 and -1, we obtain this expression, which gives us the expectation value average of this operator U, as indicated here. So to implement this average function calculation, we map the results of our measurement to their corresponding eigenvalues, and then subtract the number of times that we measured 1 from the number of times that we measured 0, and divide by the number of total simulations for our circuit. And once this is done, we obtain both the real and imaginary components of our time evolution operator. So how do we execute this for our particular system? First, we need to convert our time evolution operator into a controlled unitary that is going to be conditioned to the state of the ancilla qubit. We generate a different set of lists that are going to store our results, and then for each given time in our simulation, we're going to compute the Hadamard test for the control time evolution operator for the initial state, and then store the result of that measurement, and post-process to obtain the correlation that we seek for U. So to construct the Hadamard test circuit, we need to perform or generate a circuit that contains both sufficient number of qubits to represent our initial state, as well as an additional qubit for our ancilla. So this is what we're doing here on this first segment of our function, where we add an additional qubit to our quantum register to be our ancilla, and add a single classical register because you're going to only measure the state of our ancillary qubit. We prepare the initial state and the state of the ancilla, and then we adjust the preparation of the ancillary qubit by including the Hadamard operation. If we are calculating the expectation value of the imaginary component of our unitary operator U, we include the phase gate, otherwise we don't include it. And then we append our time evolution operator a given number of times such that we reach the current time t, because our time evolution operator corresponds to a given time tau. So if you apply tau n times, you reach time equals to n tau. And then we undo the ancilla superposition state, we append a barrier, and then perform the measurement of the ancilla and return the complete Hadamard test circuit. We proceed to execute it in a similar way as we did for our state vector approach. And if we plot the results of the Hadamard test to calculate the survival amplitude, we obtain agreement with the benchmark as well as the state vector results. So it can be noted that the results agree with the green dots and the red crosses agree, but we have some small deviations at some particular times. This is due to the number of times that the circuit was executed, and if you want to perform this right 1,000 times, 10,000 times, you can obtain much better statistics for each value of our observable at any given time. So this is how you can perform the simulation with both the state vector and Hadamard test approaches. So what did this presentation cover? In summary, I've demonstrated how you can construct this Hamiltonian operator as a sum of tensor product of Pauli matrices within the Qiskit framework, how to construct the star approximation of the time evolution operator, how to compute the evolution of this initial state to a time evolved state by applying the time evolution operator to a given initial state, how to execute this combined circuit to obtain our final state, and then how to compute the observables using both the Hadamard test and the state vector approach that allows us to calculate correlation functions of unitary operators. As mentioned before, the code associated with this particular presentation is made available at the CCI website for the Center for Quantum Dynamics on Modular Quantum Devices. Let me know if you have any questions. You can reach out to me by email, and I'll be happy to answer any questions that you may have at any time. Thank you for your time. Have a wonderful day.